oggi. Perché andare avanti non vuol dire seguire una sola direzione, ma trasformare idee in soluzioni. Quelle di Plenitude ed Anylive che si completano nella famiglia Eni, da energie diverse, un'energia unica.
Ci sono valli in Romagna, dove la luce del sole attraversa antiche foreste e l'acqua nasce da sorgenti limpide e cristalline, dove le persone sono accoglienti, i borghi ricchi di storie da raccontare e la bellezza della natura abbraccia ogni cosa. Sono terre del fare, esperienze e itinerari che toccano arte, cultura, benessere e buon cibo. Ma sono anche terre dalle infinite emozioni. Meraviglia, adrenalina, libertà, crescita e scoperta senza fine. Certo non rimane in superficie, perché così è la Romagna, dentro. La terra che ci metti un po' a nuotare e passi il resto della vita a scoprire. Questa è la Romagna autentica.
Questa è una storia fatta di energie diverse, nate per sorprendere.
Eccoci arrivati al settore della distribuzione dei...
Partite da lontano, vanno avanti ancora oggi. Perché andare avanti non vuol dire seguire una sola direzione, ma trasformare idee in soluzioni. Quelle di Plenitude ed Anylive che si completano nella famiglia Eni, da energie diverse, un'energia unica.
Ci sono valli in Romagna, dove la luce del sole attraversa antiche foreste e l'acqua nasce da sorgenti limpide e cristalline, dove le persone sono accoglienti, i borghi ricchi di storie da raccontare e la bellezza della natura abbraccia ogni cosa. Sono terre del fare, esperienze e itinerari che toccano arte, cultura, benessere e buon cibo. Ma sono anche terre dalle infinite emozioni. Meraviglia, adrenalina, libertà, crescita e scoperta senza fine. Certo non rimane in superficie, perché così è la Romagna, dentro. La terra che ci metti un po' a nuotare e passi il resto della vita a scoprire. Questa è la Romagna autentica.
Sì, va bene.
Questo è un luogo che genera dialogo,
Qualcuno che si impegna, che si batte.
che approfondisce la conoscenza e sostiene la fiducia. È un crocevia dove si incontra chi desidera il vero, il bello, il giusto e il bene. È una testimonianza di speranza nel cuore ferito del presente. E tutto questo esiste anche grazie a te.
Buongiorno.
Good afternoon. Welcome. Would like to welcome to you all to this meeting entitled Materials That Did Not Exist, Inventions and Discoveries. Welcome to the Rimini meeting. Throughout human history, many eras have been marked by a particular material. Think about the Copper Age, Bronze Age, the Iron Age, which began 6,004.5 and 3,300 years ago, respectively. In particular, why are these eras called like that? Because there was a specific material which was the key material. Man learned how to process it, and the times for the transformations. In the past, these transformations took place much more slowly. If you think about what happens today, the timing is definitely different. It is faster, much faster. The times for these transformations are very rapid. Think about the fact that the plastics which has become the key material of the last decades, is a fundamental material. So technology changes, the rhythm, the pace of changes a lot. Think about the pharmaceuticals, materials created in laboratories that did not exist in nature, or materials, nanoparticles, catalyst materials, many materials. So think about a metal alloy such as steel, which is a mix created by iron and a small part of carbon. Without the steel, the Industrial Revolution would never have taken place. And there's a very fine control when it comes to these technologies. Just by changing the fraction of carbon, linking with iron, you don't have steel. Superconductor materials are working with very low temperatures, enabling experiments, international experiments, such as those conducted in the CERN. From the point of view of the knowledge and manipulation, for several decades now, humans have been able to see and engineer materials down to very small scales, atom, particularly at the atomic scale. And here too, a new world is opening up for exploration, far from our usual macroscopic and contingent perceptions of things. We have a macroscopic perception of things, but we will see today with our guests that there is a very profound link between the atom scale part of the materials and the properties of the materials that characterize every day our own lives. To try and enter deeply these topics, to learn how these things work and what are the implications for scientific knowledge, our culture, and our behaviors. We have two guests today. We were supposed to have three guests. Professor Liberato Manna, unfortunately, cannot be with us in person, coming from the Italian Institute of Technology, and he's stuck in Canada by the biggest strike of air transport employees, the biggest strike of the last decades. But if you want, you can listen to his contribution he will be connected during the exhibition in A5. Fortunately, we have Professor Marco Beghi, Professor of Physics of Matter at the Milan Politecnico University. And we are going to see his slides. And then we have Professor Silvia Gross. She's full professor of Inorganic Chemistry at the University of Padova, and Mercato Fellow at the Institute of Technology in Germany. Thank you for being with us. I will ask each of them a question, asking you to speak a little bit about your personal career, so telling us what you deal with and what are your passions in your everyday work, and then entering into details. Marco, let's start from the beginning. What is the material? What determines its diffusion, its dissemination? And is a material invented or discovered? Thank you for your answers. Thank you very much for having me. Just to give you a couple of coordinates, my personal story is a mixed one. I work as a physicist specializing in materials, especially thin films measurements. As you know, the title of this year's meeting is "We will be with new bricks," and this spurred our association to organize the exhibition called Homo Faber. The accent, the focus is on new bricks. What I would like to do in this introductory presentation is to set a sort of perspective. So reading the sentence, we will build with new bricks. So the new bricks are used to build. This is their function. So in this slide that you can see here, the starting point is the natural raw materials. So the natural data that we have. In the second line, you see the secondary, second materials. The possibility to use materials that do not come, that come from the urban mining, as she called it, so the waste material. So the purple areas are technologies. So from the raw material generally is not a material that can be used. What is needed is technology in order to make it a usable material. And in turn, the material is the input for other technologies that are used to produce devices, structures, tools, etc. So a material is used if it has the useful properties to carry out specific tasks. Indeed, usually the material being used is the material which has the proper compromise between various requirements, which in many instances are juxtaposed to one another. So if you manage to find a reasonable balance between these requirements, you can use the material. The material and the finished products, so structure, devices, etc., are the result of a technology. They are industrial products. Therefore, they are evaluated in the way industrial products are evaluated. So the criteria are efficiency, effectiveness, the cost effectiveness, the sustainability, which 50 years ago was totally ignored, but which is becoming increasingly relevant and important. Criteria with which you evaluate an industrial product, and the cost and the fact of being cheap is one of these requirements. We teach our students of material engineering that there are two key sectors in which new materials are developed and implemented: the military sector and the sport and leisure. And these are the two sectors in which the cost is a secondary aspect. Obviously, in the military sector, and when it comes to sports and leisure, it is also not a fundamental element. If Yannick Sinner used a tennis racket of a particular material, everybody would buy it, even if it was very, very expensive. So these are the two key sectors. So the success or the lack of success of a material is determined certainly by its own intrinsic properties. The material has properties enabling it to meet several requirements, but it is also determined by the technology upstream, enabling to produce that material, and the technology downstream, enabling to reach finished products. There are many examples of materials with very interesting properties that were not successful because either when it comes to the production and use technology, it was not possible to obtain a fully adequate technology. And Professor Liberato, who is not with us, when we talk about nanomaterials, clearly almost everything is determined by the way in which you assemble the material. As Francesco said earlier, small differences in the productive process at times are enough to determine the fact that a material may be used or not used. So just to start by giving you an example, when we talk about materials to build, we talk about solid materials usually, but this is not always the case. Let's start from a material which is gaseous, technical gases. In various processes, some gases are used, which are used as chemical reagents. So, just to give you an example, in the semiconductor industry, there are many processes in which some elements are made diffused in a substratum. This is a silicon substrate, which is the basis for many electronic technologies. High temperature chamber, you inject a gas, and the atoms penetrate and they disseminate in the substrate. At times, they penetrate through a very thin substratum, but this is enough to give to that stratum, to that layer, the properties determining the functioning of the device. And in this sense, that gas, sorry, so in this sense, that gas is also a construction material. So when it comes to gases, we have many degrees of purity, different grades of purity, and 19.99 called this is based on the number of nines that you see here. So if you have a gas with 6 nines, 1 part per million of purities, if in that gas there were 10 parts per million, it would be enough to say that for that specific process, that specific gas is not suitable. So to move on to another material, which is also another material for construction in many processes, but in this case we focus on the processes in which water is not useful for building, so we focus on water. Water sent from a source. Water coming from our tap is an industrial product in the end. And then I will mention another industrial product that is used in another context. Why is it an industrial product? Because as I state here, the water that we drink is subject to a series of checks and controls and manipulations in a sense. Processes correcting its properties, not to forget the fact that the installation and the tubes taking water to our tap is a first level industrial plant. And here we have another application of water in thermal electric plants, so steam turbines. Think about the steam turbines. So there's a boiler heating water, high temperature, high pressure steam, igniting the turbine, then the generator giving electricity. In steam locomotives, the exhaust vapor steam will exited from the chimney of the locomotive. In this plant, the steam continues to cycle. It is recovered. So this water is an industrial product too. It is different from the drinking water. In particular, drinking water needs chlorine for sanitation purposes. If we used this drinking water in the energy plant, this would cause disastrous corrosive effects. And if in the water of the steam plant, certain organic residues would be tolerated, which would make water not drinkable. So the same water gives rise to two different industrial products which cannot be exchanged with one another. If we talk about water, we cannot but talk about wine too. Wine, in the first instance, is water with an 85% grade of purity. And the second approximation, it is a mixture of ethylic alcohol and water with 99% purity, maybe 19.5% purity, maybe. This means that the difference between a common wine, and a prestigious wine is all in that 0.5%, which determines the difference between common wine and a very prestigious wine. Another example has to do with semiconductors. So all the cheap, the integrated circuits, the majority of what we use today are built using silicon. About 40 years ago, many people said silicon would be replaced by gallium arsenide, because gallium arsenide, which is also a semiconductor, the mobility of electrons is greater, and therefore you obtain faster devices. And so many stated that silicon would be replaced. This did not take place. Why didn't it happen? Because the gallium arsenide, which is a compound, whereas silicon is a single element material, it was not possible to develop a production technology for a gallium arsenide so much as to have perfect crystals and produced at a very large scale. So the arsenide did not actually replace silicon. The objective was that of making devices faster, and this aim was achieved by developing the construction, the building technology of devices on silicon, in particular by making the devices smaller and smaller. Obviously, having a smaller device enabled to move from the first very big mobile phones, and we have a mobile phone now, a smartphone in our smartwatch. So this is the effect of miniaturization. The other stimulus for miniaturization was that the small devices are faster for two reasons. The first one is that the signal needs to cover a shorter path to reach the various devices. And secondly, the individual devices, I will make an analogy. The device needs to get a certain amount of charge. If the device is smaller, the amount of charge is smaller, and this can happen in a shorter time. So as you see from the graph tells you the density of devices. In particular, this refers to transistor density. Over the years, at one end of the curve, you see that the most recent date is 2020, is 100 million of transistors on 1 square millimeter. This is what has been obtained, and this is what underlies the fact that the devices are working faster and faster. So to go back to the title of this meeting, is it an invention or a discovery? Well, the discovery is a discovery of a new phenomenon which is unforeseen. Nobody was looking for it because nobody imagined that such a thing could exist. The example I make is the superconductivity. Nobody could imagine that superconductivity could exist. Gamma-Lingons was the first one to liquefy helium, measuring the resistance to lower and lower temperatures. He discovered something he did not expect. Electrical resistivity collapses to zero. This is a pure discovery made possible by a technological advancement, progress. It was made possible by the fact that he managed to liquefy helium, which was a result never obtained before. Once the phenomenon was discovered, then it is possible for the invention to take place. And the invention aims to obtain the phenomenon in a more evident way, in a more reproducible way. And so there's a space for understanding the phenomenon, understanding in which conditions it occurs, and then the conditions to use it effectively. So we already mentioned superconductivity, and we will get back to that discovery. Let's think about another example in which the discovery was not unforeseen. It is a result of something pursued for dozens of years. The sensitive glasses, the touch screens that we all have in our smartphones. 40 years ago, or maybe 50 years ago, alas, the computer terminals, screens were only included text, so you needed to interact with the computer through strings, through writing. You didn't need to touch the screen. Then, about 40 years ago, the Macintosh, well, was the first one to have a very powerful graphic interface. When you have a powerful graphical visualization, there was a need. It is easier if I touch a screen instead of typing strings. How can you do that? You need a sensitive glass. It took dozens of years. I have no idea of how much money was invested in order to be able to obtain a touchscreen. In that sense, we can say that the touchscreen is an invention. It is a result of a targeted effort, a stubborn effort, which lasted for dozens of years. Getting back to the materials used for construction. Well, up to several thousands of years ago, metals were not known and they were not used. Wood, stones were used, terracotta was also used. So we have archaeological coins dating back to over 20,000 years. They were made of terracotta. It was a world in which, well, these were the material, the solid materials that were available. There was no other material available. The very first metals to be used was gold. One of the first metals to be used was gold. We all know that gold is a material that does not get rusty. It does not oxidize. And in nature, you may find gold nuggets. All the other metals, as we know, oxidize and they get rusty. So in nature, you cannot find aluminium or iron nuggets. Even if you found them, they would be oxidized. So you would see the mineral, which is typically an oxide containing the metal, which apparently has the texture of a stone. When it comes to gold, gold does not oxidize, and therefore, although they are not so easy to be found, you can find gold straws or golden nuggets. So what does this mean? In the case of gold, the first passage, so from raw material to material, the first step is skipped. Of course, you need to melt the gold, you need to refine it, but it is already available as gold. So just imagine a world in which you had wood, flint, stone, terracotta, and a shiny material such as gold, which was also very ductile. Gold at the beginning was very precious, and only because it was rare, but also because of its properties. Gold is too soft to be used to make a knife. You cannot manufacture a golden knife. So gold has always followed its own trajectory. It was used for decorations, for jewels, etc. Just try and imagine the marvel of our ancestors. You can only try to imagine that. Using furnaces and melting pots, you see the pictures in which there was an attempt to reproduce the prehistoric way of melting metals. Those who managed to create melting pots or furnaces to cook terracotta, to bake terracotta, they discovered that using strange rocks beneath the stone, or at the basis of the stone, they saw a very hot liquid material, which then became solid and had specific properties. The process through which this happens is the same process still being used in the furnaces. You introduce an oxide, which is a mineral material. It is round and mixed with carbon. Carbon plays a double role. On the one hand, it burns and so it raises the temperature. On the other hand, it is also a chemical reagent. Carbon takes away oxygen from the metal, copper or iron, and it leaves the reduced metal, melted metal, that can be used. So this is a succession of pictures. So the first metal to be used was copper. Copper oxidizes relatively in a relatively scarce way. It is used for several parts of buildings, and it is also possible to find some copper nuggets. We don't know whether the copper was used because several nuggets were found. However, it was the first metal to be used by man. Copper is not too effective. It is too soft. You see an X by the Milano man by Ötzi. It had a copper X. You cannot make a sword with copper because a sword would be too long and a copper is too soft. Once you discover that there are stones which, when processed, can give rise to copper, well, this gives rise to invention. And probably, after several attempts, after finding the best conditions and the best ingredients, bronze was discovered. Copper and tin. And so this led to iron. Then iron melts at a greater temperature, so the steps towards iron was made possible by technological progresses, the creation of furnaces reaching higher temperatures. And just think about the advantages of the metal vis-a-vis the stone. If you want to make a shield made of stone, well, a granite shield is an excellent protection. But then using a granite shield would be very difficult because granite is very heavy. So the metal has this tenacity and this possibility to become a very thin layer, so it can be processed so as to achieve a whole set of applications that is not possible with other materials. So we also talk about other materials to build, so stones and bricks. To build walls, stones are very resistant, they are sound, they are robust, they resist rain, they resist winds. So you can make stone walls. You can use raw stones to make walls. In this case, you have some problems to face. The walls are not regular if you use raw stones, and then you also have a problem with resistance. Because if you use raw stones that are irregular, you also need to use a big amount of mortar, and these raw stones do not lean so well one to the other because they do not have the resistance of the stone is not the same. The mortar, the lime is used and for these walls. If you cut the stones and you obtain regular stones, as the ones you see on the right-hand side of the slide, these can lean one to the other very well, and so they can be used to build a wall. However, cutting a stone is a very complex process. It is a long process and expensive process. So what is a brick? A brick is the possibility to have a cut stone without the work to cut it, because terracotta was already known. Brick is terracotta being processed. When it can be easily processed, it is then placed in a mold, and then baking it, it gets almost as resistant as a stone. And therefore, brick is a possibility to have a cut stone, a regularly cut stone, without all the work to cut it, which is one of the benefits of metal, one of the advantages of metals, for totally different reasons. If we create a mold and we pour the metal in the mold, we obtain the object of the shape that we want by processing the material in its liquid state, which is the simplest state to process a material. This is one of the reasons for the success of plastics. Plastics is very easy to process when it is in its fluid state. So it's very easy to obtain complex shapes with plastics because it is processed while it is still fluid, and then it takes on its solidity. Then houses are no longer built with bricks. The title of the meeting is already aged, so to say. Now a fiber plasterboard is used. Why is this new material used? Because it has better characteristics. In a sense, there's a greater possibility to modulate the features of the walls. But the decisive advantage of fiber plaster is the technology, which is much faster. Installing plasterboard panels or fiber plaster panels is a very rapid work, and no water is needed. So a wall made of bricks dries in months, whereas a wall made of plasterboard does need no time for drying. Well, I would like to stop here. I have another slide to show you. It is important. So we talked about superconductors. On the left-hand side, the same picture of a Camerlingones discovering that the resistance, electrical resistance of metal at a low temperature is completely disappears. This was a discovery, and so that was a room for invention. So just to give you an idea of what invention means. These are filaments. They are threads of superconductors. You cannot create a thread simply with a superconductor. It needs to be cooled down using liquid helium. It is very difficult. But above all, the pure thread of a superconductor is risky because if we have a thermal fluctuation, it loses the superconductive power, the energy disappears, and it becomes an enormous conductor. So for a thread of semiconductor, you need to have lots of filaments of superconductors drowned in a metal such as copper, so that if one of the filaments has a conduction problem, a copper immediately redistributes the current to the other threads, so it is stable. So this is a thread that is used to make the bobbins, the reels that are used in the CERN, and that will also be used in another work. And they are used. We have a metal which is an intermetal material, which tends to break. So in order to obtain some which can become a thread, the work is the one you see here. So this is a section of a thread of superconductor. So if you look at the bar, it is 1/5 of a millimeter, 0.35 millimeters. That's a diameter within that thread. This is one of the processes and not the only one. As you can see, there are 192 tubes of a material, each of them filled with tin powder. So superconductivity is a discovery. But in order to make one thread like this, 190 very small tubes within a a thread of half a millimeter takes a really advanced technology. So this is a last slide. We can talk about it maybe tomorrow. This is a slide with a conclusion. I just want to summarize a little bit my presentation. With the growth of the comprehension of the understanding of behaviors, the performances required to materials, and the ability to manipulate the material, research and development of new materials, we've shifted from these empirical experiments to the systematic use of knowledge, methods, and scientific instruments. So this is my conclusion. Thank you very much.
Ti ringrazio di aver...
Thank you very much for your very clear description. So pay attention next time, because 0.5% makes a big difference between a good wine and a bad wine. Thank you for making us understand that details are important. I was fascinated by the story of Velcrum, which already existed, and when we started to make it with plastic, it became very popular. That's a small detail, but that can make a big difference. Now, let's focus on the materials themselves. As you were saying when describing the superconductive alloy, you were talking about some details about the atomic scale. Chemistry is very important, and especially the technology developed to achieve some aims, to make touch screens, and oftentimes technology requires time and creativity. This is why we have invited Silvia Gross. Silvia, tell us what you do, and then tell us about this creative approach used to work on materials and raw materials, to take them where they are already used. You deal with the circular economy and technologies and chemistry. So tell us something about the link between the chemical properties of these materials and good and effective ways to recover them. Hello, good afternoon, everyone. Thank you very much, Francesco, and to the organizers of the meeting for inviting me here, and thank you for being here. Yes, I am an inorganic chemist at the University of Padova. I'm dealing with the synthesis of materials, sustainable synthesis especially, but I also have the honor and privilege of coordinating a degree course, Chemistry and Sustainable Technologies for Circular Economy. So in recent years, I worked with colleagues from other sectors, and I started dealing with the recovery of critical raw materials that I'm going to talk about this afternoon. As for the title of this session, Materials That Didn't Exist, Inventions and Discoveries, I wanted somehow to change the perspective and start from a different approach. Start from materials that already existed and are becoming scarce and critical, which is now necessary to recover, as in critical raw materials. So what are critical raw materials, and why are they important for ecological transition? And what are the tools to manage these critical raw materials? What can we do? For example, we can recover, reduce, or replace. Then I will talk about urban mines as against the natural mines. And I will talk to you about the approaches to recover critical raw materials. And I will talk to you also about what we do in Padua and the open challenges, many of them, and future prospects. Now, these are critical raw materials. Following up to what the previous speaker said, we depend on the use of materials, elements, and chemical compounds, and that has exponentially increased from the Bronze Age to the Industrial Revolution. The technology developed by man over the centuries has become increasingly dependent on the dependence on materials and especially metals. And this is also reflected by the beginning of an article produced by the JRC, a research institute based in Europe, producing technical and scientific data needed by the European Commission to develop laws and regulations, then discussed by the Council of Europe and the European Parliament. In a 2023 report, the beginning has a very meaningful sentence. Energy transition, the renewable energies, energy transition is a transition of materials. A clean energy system based on renewables is much more intensive in terms of use of materials and metals versus compared to traditional energy. This is quite interestingly quantified by this graph showing the content of some metals, chrome, for example, in a traditional car compared to an electric car. In an electric car, there are many more critical raw materials. In the battery of an electric car, for example, there's about 90 kilos of critical raw materials compared to traditional cars. And they also used many magnets. They are also critical raw materials. So for renewable energies, a lot of materials, critical raw materials are used. The European Union pays a lot of attention to this topic. Every 3 years, since 2011, a report is published by the European Commission taking stock of critical raw materials. So the next one will be published in 2026. What are critical raw materials? The European Union identifies them according to two basic parameters. First, their importance for strategic technologies. And second, a risk of supply interruption, which doesn't mean that we are finishing the mines, but that the supply risk may also be connected to political tension and geopolitical situations. And we've seen that during the pandemic. Many mines of critical raw materials are in countries with which we don't have, let's say, idyllic relations. There are 15 strategic technologies for the EU. Renewables, technologies, data, airspace, defense, industry, and electrical mobility. So fuel cells, wind energy, drones, missiles, satellites, robotics, clouds. There can be geopolitical tensions. As I said, this is a map showing the main countries providing critical raw materials, as in Russia, China, which has a monopoly for many critical raw materials, especially rare earth. And Europe is not very blue here, but there is a problem of resilience and a response by the EU to the supply of critical raw materials. Every 3 years, the EU produces a list of critical raw materials. This is 2023. where strategic raw materials were introduced. For example, nickel and copper. Copper, we all know copper. And nickel, which is not yet critical, but since it's being used massively for the electrification of copper, they could become critical. Here, there are also some chemical compounds and groups of elements, especially rare earth, platinum, and so on and so forth. This list changes every 3 years. It is updated every 3 years. What is not very good is that from 2011 to 2023, this list got longer and longer. The number of critical raw materials is increasing because they are increasingly used also due to ecological transition. So the European Union is now wondering how can Europe solve this critical problem. In 2023, there was a draft regulation, which then turned into an official regulation of the EU in 2024, which is the Critical Raw Materials Act. According to this regulation, the aim of the EU is to become more resilient and therefore to have at least 25% of critical raw materials used in Europe coming from recovery, as in secondary or recycled raw materials. Another interesting topic is that the EU says that we should reopen the mines that were closed 50 years ago. And we should start again exploring mining in Europe. For example, a very important deposit of rare earth elements was discovered in Norway and Scandinavia. The terms of rare earth elements come from Itaby, which is a village in Sweden. So this word is often used in geopolitical tensions. So rare earth, which is not critical raw material, but a subgroup of critical raw materials. These 17 elements of the periodic table, whose magnetic and properties are very important. Wind turbines, for example, are working with one of these rare earth, neomobium. How to deal with criticalities? There are different strategies, and one is to start studying elements, the chemistry of elements, once again, because they are a vital tool. This is not by chance that I'm here. I'm an inorganic chemist, and I'm studying chemistry. In color, you can see all the critical elements in the periodic table. So, in practical terms, what can we do to reduce our dependence on third countries exporting critical raw materials, which maybe do not have very good relations with Europe? Now, first and foremost, we should design materials and devices so as to extend the lifespan of the product or to minimize its use. So it's not just the fact that you don't have to change your mobile phone or tablet every 2 years, but also to design mobile phones and tablets so as to minimize the consumption of critical raw materials. For example, this is a nanoparticle, which is a core shell. What is a core shell particle? Think about an orange. You have the skin and you have the inside. The whole orange is not just made by one critical raw material, but the inside is made, for example, by a metal, and only the outer shell, only the orange skin can be made of critical raw materials, so that you do not consume too much. And then there is also another approach, which is replacement. You have heard about sodium batteries, which should replace lithium batteries. Lithium is very critical as an element. Sodium is much more abundant. And here, there's the problem of replacing one metal with another one, while keeping the same characteristics and performances. Here, a lot of knowledge in chemistry is needed. And then there's the problem of recovery and recycling. And I'll mention about that later on. As for the role of inorganic chemistry to recover and recycle, replace, and reduce the use of critical raw materials, there is a very wide literature. With a colleague of mine, we were the editors of a collection of articles on this topic, where recovery and critical raw materials were discussed deeply. And there's a lot of scientific literature on this topic, as I said. Inorganic chemistry, which, for example, deals with metals and their reactivity, is a methodological and experimental tool, not only to recycle materials from waste, but also to find new methods with lower impact to dissolve metals. So if you have to recycle materials starting from waste or industrial waste, there's a first step, which is some sort of mechanical step. So you take the object, for example, your mobile phone. It is disassembled into different parts. Then there is some mixing. So you reduce the size of these materials. They're turned into dust. And then you enrich the metals with different approaches. For example, separation by density, or the use of magnets, and so on and so forth. Once the metals have been enriched, there are different methods to separate these metals from these matrices, which are quite varied. They do not only have and contain one metal. Maybe there is still some plastic residues. So you can, for example, use very high temperatures, over 1,000 degrees, to melt metals and then to refine them. Whereas the chemical method is hydrometallurgy, where you use very aggressive substances, nitric acid, sulfur acid, to melt metals and separate them. And then the final step can be made through other processes based on the use of electricity. So there are different approaches. There is already state-of-the-art, but they all have pluses and minuses. Some are more intensive in terms of energy use. The first one requires a lot of energy because we need very high temperatures, whereas the other one produces a lot of water, which is contaminated by very aggressive agents. So there are pluses and minuses for all methods. Now, let's now focus on urban mines. What are urban mines? Well, they are basically the recycling areas where citizens go and throw away electronic and electric waste. Like, I don't know, the mixer or tablet or your mobile phone. So in these urban mines, which have to comply with different regulations for collection, we collect all this waste, which has a lot of advantage because they contain a lot of critical raw materials and other types of materials. So as against a natural mine, the urban mine is a collection of human waste and has a fundamental advantage compared to rare earth elements. They are located in our cities. They are close to us. This is something that we Europeans can use without depending on third countries. And urban mines are very important for different reasons. First, these waste, as in small households, appliances, big household appliances, electronic devices, lighting devices, are produced significantly. This is for Italy. Every Italian citizen produces at least 6 kilos of such waste every year, without considering what we have at home in our drawers that we don't want to throw away. Then, when you extract 1 ton of rocks from a mine, because of the increasing reduction of the presence of metals in minerals, you can, in the best case scenario, extract some grams of gold, some grams of silver, and some kilos of copper. As for the rest, they stay there. So there's a lot of waste. On the contrary, if we were able to enhance and use all the metals in a mobile phone with a weight of 200 or 300 grams, from 1 ton of mobile phones, we would be able to extract 100 times the quantity of critical raw materials. Then we have the mines here, and the concentration in metals is very, very high, 150 times higher than rocks. Then the mining extraction from the mine, requires a very high energy use, which is much lower if these metals are extracted from the scrap. So extracting metals from waste, from scrap, requires a lot less energy and produces less water compared to extracting the same metals from mines. So we have it in the cities, a much bigger concentration of metals, less energy consumption, less wastewater produced. So the exploitation and use of urban mines has a lot of potential. Europe only has one option. Now we are starting exploring mines in Italy once again, but the problem is that we cannot extract a lot of critical raw materials. So even the impact of mining has to be considered. So the point is to take these metals from waste, like, for example, cars at the end of their life cycles, everything that is thrown away. In a mobile phone, you don't have gold, but you have gold together with aluminium, carbon, silicon, copper, and so there's many different types of waste. There are some parts in plastic. There are some ceramic materials which are very resistant to high temperatures, and some other materials. In your mobile phone, for example, there's from 30 to 40 elements that you can see here. How can you separate them? Because you don't want to have 30 metals all together. You want to separate gold from silver, copper, aluminium, and so on and so forth. So selectivity is important. You need to separate all the different elements. But chemists are developing some molecules that can capture selectively only one of the metals. Jason Love, for example, was able to extract from mobile phone scrap gold in a selective way. Hence, selectivity is important. So it is important to study because you need to study the molecules to separate the different metals in a selective way. We are also working on that in Padova in a PhD thesis where the copper is being studied. Copper will become strategic because copper is used everywhere. 83% of copper that is used is extracted by mines, 17% is extracted from industrial waste, scrap, brass, and so on and so forth. However, the primary production from mines is not sufficient to meet copper needs over the next few years. I think you've heard that copper cables are being stolen, so copper is becoming very, very crucial and critical. So we need to increase the circularity of the process and recycle copper. This is the exponential increase in the use of copper in the past 120 years. In Padua, we are trying to extract the copper from scrap and industrial scrap. There is also zinc and aluminium by using a different approach. Not acids, because they're very corrosive, but by using weaker acids, organic acids, for example, the apple acid. And this PhD student, for example, took malachite, which is a copper compound, and produced complexes to extract the copper. The compound made by, in the end, is called copper sick, which is somewhat funny. So we're trying to recover lithium, nickel, and manganese from the black mass, which is a black dust obtained from an exhausted lithium battery. We're doing this with some colleagues and some PhD students. And we are using innovative solvents, which have already been used, to recycle the black mass. They are called deep eutectic solvent. They are made by an acceptor and a donor. And when you put them together, the mix of A plus B has a lower melting point than A or B. So they can be liquid, they can stay liquid for a long while. They've already been tested for recycling many metals. And then you can choose the acceptor and the donor from different natural substances. So you can change A or B to melt metals in a selective way. So this is an alternative approach, a more sustainable approach for recycling metals from lithium batteries. And basically, this is the black mass, which is this black dust from the battery. We put it inside these solvents, and we try to separate metals. The approach is quite interesting. There are promising and interesting results. The different metals here are extracted with different yields. There is still the problem of selectivity, especially when chemical elements have similar properties. Which leads me to my conclusions, which and I hope that my presentation was interesting for you. There are many future prospects. We are poor of minds, but we have a lot of creativity and we are smart to develop different approaches, alternative approaches for a more effective recycling of critical raw materials. Then there is another interesting approach that the PhD student tested in Germany, whereby you use microbes and bacterial producing metabolites, which can be used to melt metals. Here, there's the problem of selectivity to separate metals, which still is a very important technological challenge. So I also put this quote from the Draghi report of 2024, and I found out the other day that Mario Draghi is going to come here at the meeting, This report focuses on the innovative potential of the EU on critical raw materials. Critical raw materials will be one of the hot topics over the next few years. There's going to be a much bigger debate on that. And Draghi said something very important, that there's a strong need for training. It's not just training for our university students, but also reskilling and upskilling of people that are already working in companies. And when they studied chemistry at the university, the concept of critical raw materials at that time did not exist. So there's an important need for training. So the university course I'm leading, starting in 2021, it was designed in 2019. And in 2019, when it was not trendy, we already inserted a university course on critical raw materials. Next year, there's going to be a very specialized course for people who are already working on that. Hence, it is important to study, as I said, as in to study and re-study chemistry and to apply it to something that did not exist many years ago. One of my favorite books, Primo Levi's books, and the chapter on nickel, Primo Levi talked about the separation of elements, and I want to finish off with that. Thank you very much for your attention.
Ringrazio.
Thank you very much to Silvia Gross and Marco Beghi. Let me follow up on what Silvia said. You were talking about a smart approach, recycling and recovery of critical raw materials. This approach is very important, even because it is connected to our responsibility, personal and professional responsibility that we all have.
Richiama la responsabilità.
It calls upon all of us. At the end of the exhibition on the new materials designed with Euresis, we can see that men, oftentimes in history, has had the opportunity to understand and to learn how to manipulate existing elements and to build new ones to meet new needs. This is why I invite all of you to visit the exhibition in A5, just close by, and tomorrow we will continue this dialogue at 12:15 with Marco and hopefully with Professor Liberato Manna, who is going to connect it with us. Silvia will leave on holiday tomorrow. Thank you very much for joining us today at this session. I remind you that all of us, each one of us, can contribute to the meeting to build this place. Every gift is a new brick helping to continue building meeting places and places of hope and beauty. Throughout the fair, you can find the stands Dona Ora, Donate Now, with a red heart. The Meeting Foundation is a third sector organization, and therefore you can deduct your donations from your taxes. Thank you very much to all of you. Thank you very much to our speakers, and enjoy the meeting. Thank you.
Questo è un luogo che genera dialogo,
Qualcuno che si impegna, che si
che
batte.
approfondisce la conoscenza e sostiene la fiducia. È un crocevia dove si incontra chi desidera il vero, il bello, il giusto e il bene. È una testimonianza di speranza nel cuore ferito, del presente. E tutto questo esiste anche grazie a te.
Questa è una storia fatta di energie diverse, nate per sorprendere.
Ed eccoci arrivati al settore della distribuzione dei
Partite da lontano, vanno avanti ancora oggi.
Perché andare avanti
Non vuol dire seguire una sola direzione, ma trasformare idee in soluzioni.
quelle di Plenitude ed Enilive, che si completano nella famiglia Eni. Da energie diverse, un'energia unica.
Ci sono valli in Romagna, dove la luce del sole attraversa antiche foreste e l'acqua nasce da sorgenti limpide e cristalline, dove le persone sono accoglienti, i borghi ricchi di storie da raccontare e la bellezza della natura abbraccia ogni cosa. Sono terre del fare, esperienze e itinerari che toccano arte, cultura, benessere e buon cibo. Ma sono anche terre dalle infinite emozioni. Meraviglia, adrenalina, libertà, crescita e scoperta senza fine. Certo non rimane in superficie, perché così è la Romagna, dentro. La terra terra che ci metti un po' a notare e passi il resto della vita a scoprire.